Hey, welcome to ProbStats 8. So in this class, we'll be looking at a very important topic, which is called normal distribution, also called as Gaussian distribution, or also called as bell curve. You must have seen bell curve. It's a pretty famous thing. Uh, so we'll be looking at its characteristics. There's a empirical rule and how to calculate the exact probability values, and then how, or rather why we standardize um, normal distributions, and then a percent point function, which is just inverse of CDF. So that's the agenda. So we'll begin. So not normal distribution, um, which basically is nothing but your bell curve, right? Symmetric about the mean. So if you fold this, if you put this on a paper and you fold this at the center, the the both sides will match exactly. Um, this is your mean, which is mu. So before I proceed explaining this one, the reason why this is so common and like a very important, or rather, it's the most important distribution um, in statistics, is because it appears in real life a lot. So, like for example, if you take humans, if you plot the heights of a large number of you need a large sufficiently large data set, then that when you plot those heights, it'll take a bell curve like this. If even the weights also, if you plot the weights of the same people, that will also um, show a bell curve. And even blood pressure, if you take the blood pressure readings, or if you take the test scores, like IQ scores or test scores, they also uh, form a bell curve. And if you take, if I say, measurements of if scientific equipment or errors, they all form some sort of bell curve. So bell curve does not mean it has to be exactly like tall and like this. It can be like this, or it can be like this, or it can be like this. uh, we already know the standard deviation, right? As the standard deviation increases, the curve stretches, and if smaller the standard deviation, the narrower the bell will be. So those are some examples. Now, if I plot, like for example, if I take the height of students, right? If I plot the height of students, the student's height, let's say, will be anywhere between 4 feet, maybe 4 feet 9 inches, to let's say around 6 feet, or maybe let's just take 5 feet to 6 feet. So, peop obviously heights are continuous variable, right? So um, so you cannot have in continuous variables, obviously, like we discussed many times, you will not know the next step. So if I say 5 feet 1 inch, the next height will be what? It cannot be 5.2 or 5.11 or 5.112. There's no there's an infinity between every two values, right? And that is why when we take the probability, so if we say, if we want to find probability of 5.11, so possible outcomes is 1, what is the total number of outcomes? That will be infinity, right? So that's why it's 0 theoretically, but in reality, 5.11 does exist. So if we plot this continuous variable of heights, right? Some heights will be so the if we plot a histogram and bucket each of these heights. So let's say maybe most common height, at least in India, I think it's around 5'7" or 5'8", right? 5 feet 8 inches. So this will be the largest bucket. Largest amount of clustering will be somewhere around here. And maybe this is 5.6, 5.5, 5.4, 5.3, 5.2, etc. This will be 5.8, 5.9, 5.10, 5.11, 5.12-ish, somewhere around like this. So this bucket will be 5 feet 7 to 5.7 to 5.8, let's say. This is the average height in India, which is most common. So that will be clustered around here. So the official definition for Gaussian distribution or normal distribution is basically it's a continuous probability distribution where the curve is symmetric, right? When we split if we draw a line in the middle around the mean, there will be 50% of the data to the left and 50% of the data to the right. And if we study its properties, like if we okay, before that, let me plot the graph just to see how it actually looks in the code. So again, we'll do our usual ceremony, pip install numpy. I already have these. Pip install pandas, pip install scipy, pip install what else? Cbol. I think that should be sufficient. So I'll import numpy, zelp, import pandas spt, import e1 as SNS, and import scipy dot stats. No. From scipy.stats import ptf. I'll be using import norm. We need the normal distribution. So the normal package in this case. So to plot, I'll do a line plot. Since we are dealing with continuous variable, I will assume my mu, which is my mean, to be around 70 and standard deviation to be around 3, right? These are just dummy values. So I can begin with my x values as np dot linspace. It is linspace, right? Or line space. It is linspace. Okay, so this takes args. Okay, so before I do this, I guess I have to explain that now. And the other features of a bell curve are, I guess let me finish the characteristics and then I'll plot the graph. So obviously the peak is decided by the mean, right? This peak is decided by the mean values, and um, what else? I want to say something. Yeah, and I guess that will go into empirical rule. I guess. Hmm. Yeah, let me talk about these. Shape is obviously, I told about shape, and the shape is dictated primarily by mean and standard deviation, right? Sigma. So, so there are infinite number of normal distributions. I showed you here, right? It can be anything like these. All these are normal distributions, and there are infinite number of them. So these are called family of distributions and family of uniform distributions. And a family is obviously, it will have the same shape, but it can have different mu and standard deviation values, mu and sigma values. Um, um, what else? So obviously the parameters are primarily mu and sigma. So it is purely dependent on mu and sigma, not primarily. It is purely dependent on these two parameters, and all variations of these will give different types of normal distributions. And obviously, if the standard deviation, the variance is, or rather, sorry, not the variance, the spread is wide, uh, you will have a narrower bell curve, and if the ST is small, then you'll have like if the ST is big, then you'll have a wider bell curve, and if it is small, you'll have a narrower bell curve. The area, so the area under this curve, the probability, the sum of all these probabilities will equal to 1. It's just like sample space. And you will get this, you can compute the probability values for this using PDF, probability density function, for area under this curve. It's like a complicated formula. Let me just show you. Uniform distribution. Sorry, not uniform. So this is the formula for normal distribution. So if you want to compute probability for at one point, you'll have to do this calculation. Anyway, so that's about the area. I don't think there's anything else to talk about area. I think that's sufficient. Yeah, and coming to the asymptotic thing, so the if you see for the bell curve, these edges taper here, right? They never touch 0. The value is never 0. This value, there's always a gap here. It's always positive. That's primarily because of that formula. It always keeps it positive because there will always be some outlier value. So you just remember that way. Yeah, I guess that should be sufficient. I don't think there's any other properties here. This symmetric, we talked about area. Yeah, let me plot the graph. We'll talk about empirical rule after this. So for I will be doing something called I will take standard deviations, which I will explain in the empirical rule. I'll just show you how the plot looks just for demo's sake. I will say mu minus 4 times st. That will be my wait. Something seems wrong. It's not linspace. Oh, it is linspace. So interval is there. So right. So I'll be taking start, stop, and the number will be start, stop. The number of samples to generate. So yeah, that will be the number of samples to generate. So I will take I'll take 100 samples plus 4 times st comma 100. So if you see this, it will generate these 100 samples, and if you see here, our mu is 70, right? So 4 times standard deviation is 12. So 70 minus 12 around 58, and 70 plus 12 around 82. So within this range, we are taking about 100 values. That will be my x value, and my y value I'll use to compute the probabilities under this curve. I'll use the PDF value, which is norm.pdf. One second, what is the signature? So it's probability density function of x of the given random variable. I think it should take random variable, the mu, and standard deviation. I think I can just drop them. 1 second. X mu st, if I'm not wrong. Yeah, so that is how it will generate. Now all I have to do is create a data frame and plot the line plot. So I'll say data equal to, I'll create a map. I'll say x values. I'll put all my x values here, and my y values here. We'll create a data frame, pd dot data frame, and I'll pass my map. So that is our data frame. Now all I have to do is just SNS dot line plot, and I pass the data as data frame, if I'm not wrong, x equal to x variable, x column, and y column. And that is our bell curve. It's just a demo, nothing too fancy here. So now we will look at 65, 88, 99 rule. So if you see in this one, I used mu minus 4 standard deviations, right? So 3 is sufficient, but here I just used 4 because for start and end, because end is not counted. No, 1 second, where was I? Yeah, so here. So for the normal distribution, the empirical rule which is nothing but 65, 88, 99 rule, 99.7 actually. What this says is, this is just a approximation. this is like a handy uh, tool for making quick estimates about uh, uh, how many data points, like or rather in what proportion of data is within these particular how do I put it, particular ranges. So what it's saying is, if we consider this as mu, our mean, so mu plus 1 sigma and mu minus 1 sigma, this is what the rule says is 68% of data will be in this range. So 68% of data will be within this range, and mu minus 2 sigma and mu plus 2 sigma, what it says is 95% of data will be in this range. Let me take a different color. So this is 95% of data in that will be in this range, and mu minus 3 sigma and mu plus 3 sigma (99.7%) data will be within this range. So 97% data will be covered in this range. So as you can see, this is just meant for approximate estimation. This tool, this is not meant for precise estimation. So it's just to quickly look at it and get a grasp of, get a feel for the data, right? And generally, if you have data points that are beyond 2 sigma, it is considered weird. It's considered unusual. And if it is beyond 3 sigma, like these areas, then it is complete outlier. These are like abnormal values. So by the way, if you see here, 99.7% data, which means there's 0.3% data distributed 0.15 here, 0.15 here, which is 0.3% data is the absolute outlier data that is there over there. So that's the main point of using this empirical rule. I think that's all there is to it. I don't think there is anything else to say here. I guess we can solve a question. So if I ask a question, what percent of data is within one standard deviation? Obviously 68%. Within 2 standard deviations, 95%. You'll get questions. I mean, you can think of questions like that. But what if I suppose ask what percent of data is okay, so I guess I'll have to take some values. So suppose I have a curve like this. These are my height values in inches. So let's say height in inches. So I have somewhere from 58 inches to, let's say, 7. So yeah, I'll take the mean as 70. So let this be 4 standard deviations away and 4 standard deviations away on the right side, which is, let's say, 82. Right, so now the mean is 70, right? So 50% of data is on the left and 50 on the right. Now if I ask a question, what percent of data is less than 68 inches? Or let's say 69 inches. What percent of, let's take 68. So what percent of data is less than 68 inches? Obviously, this rule cannot answer it, because if we take mu as 70 and standard deviation as 3, so plus or minus 1 standard deviation, the interval will be 67 to 73, right? So to say 68% of data will lie within this range, we cannot really compute what is the percentage of data that is less than 68 inches. Actually, let me not take 68. I think this will confuse you between the percentages and this one. So let me take some other example. Let's say I don't know what values blood pressure is in, but let's just say the median blood pressure is 400. I don't know if that's true or not. Just it's just random values. 400 BP, and so here my mu is 400 and standard deviation is, let's say I take I'll take standard deviation 20, suppose. So so my first my one standard deviation will be within 380 and 420. 2 standard deviations, 360 and 440, and 3 standard deviations, 340 to 460, right? Now suppose I ask a question, so rather we want to know what proportion of data is less than is less than let's say 392, right? So the question is asking less than 392. So let's say 392 is somewhere here. Less than 392 will be all of this data, right? It's all of this data. But so in this case, the empirical rules are pretty useless, because they only tell us within particular ranges. So this is 1 SD, this is 2 standard deviations, and this is 3 standard deviations, right? This will not, none of these will tell us about this area. So for that reason, we use something called z-score to get the precise probabilities and convert them to proportions using something called the z-table, which we will see. So z-score is basically, the definition is how many standard deviations a data point is away from the mean, right? How many standard deviations a data point is away from the center, which is the mean in this case. And this is for normal distribution. The whole purpose, in fact, of z-score is it's actually meant to standardize the normal distribution. We'll see what that is. But before that, let's solve this question. Then we'll go into standardization. So so the question is, suppose so the height of people is Gaussian with a mean of 65. So it's clearly giving us the height of people is normally distributed with the mean of 65 inches and a standard deviation of 2.5. So it's asking what fraction of people are shorter than 69.1 inches. Right? So to solve this, we use z-score, which is used to get the exact probabilities, and from that probability value we will get our proportion, fraction, percentage. They're all the same. So if you see the question, we can reframe this question as 69.1 is, what is the definition of standard deviation? How far away a data point is from the mean, right? So mean plus how many standard deviations away. Let's call that the number of standard deviations as z, just a variable, and our standard deviation is 2.5. So basically this is mean, which is 65 plus z times 2.5. So we can solve this by saying something like 69.1 minus 65 by 2.5. This is basically our z-score formula. This is nothing but if I take this one, this is what? This is our x, right? Our variable equal to mean is mu plus z is our z-score times standard deviation is sigma. So if I rearrange this, so this will be nothing but x minus mu by sigma, which is our z-score. So this is the formula anyway. We will use this to get the exact probability. So in this case, the exact probability will be what? 69.1 minus 65. So that's 4.1 by 2.5. So that is 1.64. So this will give us 1.64. 1.64? Yeah, 1.64. One second. Okay, so we use this to calculate the proportion. Something is off. One second. I think I am not saying it right. But okay, so I guess I made a mistake. So 1.64 is not the probability. 1.64 is the z-score. Just that's the z-score. We'll find the probability using this z-score. Yeah, that's the mistake. Anyway, this is just z-score. Don't this is not probability. Obviously probability cannot be greater than 1. So we are finding out the probability using this z-score value. Um, so to or rather, why are we using this table to find the probability? I mean, we can use the, like I said before, to find the area under the curve. We have to use PDF value, right? Probability density function. So the reason we are using the table is obviously because the PDF for normal distribution is hard. We saw this. To find this, we have to now calculate all this, plug in these values and calculate using this formula, which is a tedious process. So what StatsGuys did was they use a concept called standardization. What standardization does is, since there are infinite number of uniform distributions, right? So all these uniform distributions, if we want to compute probabilities for all these types of varieties of uniform distributions, that is like an impossible task, right? Or rather, it will be too tedious. It's basically so to avoid that, what statisticians did was they decided to standardize all these normal distributions into one single normal distribution called standard normal distribution. Excuse me. And so that is the whole purpose of z-score. The whole point of z-score is to standardize all these normal distributions to make computation, calculating the probabilities easier. So what they did was they converted all these variable units of a normal distribution. So let's say we are taking heights here, right? This is heights. So here we have, let's say, 58 to maybe 82. We have all these heights here. Now what standardization does is it sets the mean value. Let's say mean is 70 here. It sets the mean value to 0 and standard deviation to 1. So when we say mean value 0, it does not mean that the actual mean is changing. We are mapping this 70 to this 0, which is the z-score 0. So let's say you have your heights and you have z-score. So all they are doing is they are mapping z-score values. They are mapping height values to z-score values. So here maybe one standard deviation. Let's say here it is the standard deviation is 3, so it will be 67 will be -1, 64 will be -2, etc., etc. And here 73 will be +1, 76 will be +2, right, etc., etc. So this is just a direct one-to-one mapping of these values. And so when standardized, the mean will sit exactly at 0. So the mean will sit exactly at 0, and the standard deviation is 1. So the values will be exactly one unit away, which is one z-score away. -2, +2, minus 3 plus 3. So these are all z-scores. Let's see, I hope that was clear. So that's the whole point. And there is only one standard normal distribution. While there are infinite number of normal distributions, there's only one standard normal distribution, and all those normal distributions are converted into this one standard normal distribution using z-score. That's the purpose of that formula. So where were we, by the way? Right. Now we got our z-score value in this. We are solving this question, right? Yeah. This is the question. So we got the z-score value. Now we want the probability. So okay, so so the whole point of standardization was so that they can create set of probability values that can be applied for all of them, and that is where the z-score table comes in. And this is the z-score table. I'll put this in the video description anyway. You don't have to worry about that, or you can just check this link out. This is the z-score table. These are all the computed probabilities for all types of normal distributions. You can use just this one table, and you have z-score, negative z-scores and positive z-scores, and of course the neutral z-score, which 0. You have z-score 0. We just saw here, right? That's the mean value mapped to it's mapped to 0. And the 0 mapping is nothing but the original mean value for that normal distribution. Yeah, so the way to check this, read this table is basically you take this z-score value, which is 1.64, and this is positive value, right? So these are all negative z-scores. So you see here z column. These are all negatives, and these are all the positive values. Now we got 1.64. So we take the first two digits, which is 1.6 here, and the third digit 4. So we check the third digit here, right? So 1.6 and 4 is over here. So this will be our probability. That is 0.94950. Right? When we normalize this will be nothing but 94.9%. So the question, so the answer to this question is what fraction of people are shorter than 69.1 inches? That will be 94.9%, around 95%. People are shorter than 69.1 inches. So that is how you solve that. Yeah, so we already checked, right? So the value z-score can take, can take positive values, negative values, and the neutral, which is 0 value. So if z-score is 0, then it's exactly at the mean value. If it is positive, that means it's on the right side of the mean, and if it is negative, it's on the left side of the mean. Yeah, one thing, I guess, now, this can be slightly confusing if you, but just to clarify, standard deviation, the definition of standard deviation is, it is the mean of all the, it's the mean, it's the mean distance of all the data points from the mean. Sorry, it's the average distance from of all the data points from the mean. That is what standard deviation is. It's the spread. Variance is also spread of data. It's the measure of spread of data. Informally, But formally, variance is just the squared units of standard deviation, right? Standard deviation is just in the normal units, and z-score, like I said before, the definition is it's the number of standard deviations away from the mean. That's what z-score is. Just to clarify. Now let's go to the next stop. We already saw why we take z-table, right? So that is one thing. Oh, okay, by the way, we can solve this question using Python code as well. We have a Python package. We already saw norm dot we already saw norm.pdf here, right? So where is it? Yeah, this is the norm.pdf. So what we can do here is we can take we can take norm.pdf here and pass the z-score value. What is our z-score value? It is 1.64, this one, right? This is our z-score, 1.64. So if we do that, we will get 0.103961. Okay, it's not PDF, this should be CDF. Actually, I think I have to correct myself here. To find the density here, we use PDF, right? PDF is probability density function. It does not give exact probabilities, that is PMF. For continuous random variables, PMF is 0, right? We already saw in the beginning. So to get the density, we got the density using the z-score. Now to get the proportion, we have to use CDF because this is cumulative distribution. So the cumulative probabilities we will calculate to get the proportion, get the fraction. So we have to use CDF here, CDF of the z-score. So CDF of z-score, because until this, so let's say the z-score value is 1.64, came somewhere around here, let's just assume. So until that point, cumulatively you have to calculate the calculate all those probability values, right? So this should be CDF, and there you go, it's 9.0.949, which is exactly what we got in the table as well, right? The table also showed the exact same thing. For 1.64, it's 0.94950. So that's how you can do with using Python as well. Simply, you don't have to check the table all the time. So we saw why z table. I hope that was clear. Now we'll solve another question. This is blinding me. 1 second. I think there is a dark mode. Yeah, but I don't think dark mode will be clear anyway. So let me use this one. So the question is, how can we find the fraction of people shorter than z-score 1.64? So here they're asking a direct technical, giving us using direct technical value, which is they are asking us fraction of people shorter than z 1.64. So they gave us the z-score directly. So all we have to do is check 1.6. And the third value is 4. So we already solved this exact same thing there. which is 0.94. So let me change the question slightly. So let's say 1 dot maybe let's say maybe 1.27. So if we look at 1.27, 1.2 this is here, and 7 will be this one. So the third digit is 7, right? So we'll use this one. So 1.2 and 07, that will be 80. That will be 0.89796, which is 89.7%, right? And if we directly use the same norm.cdf and pass the thing 1.27, the z-score, you see exactly 89%, 0.897. Let's solve another question. The question is, balls produced by manufacturer have a mean diameter of 50 mm. So let me note the values. So the mean is 50, right? And standard deviation is 2. What would be the diameter corresponding to the z-score of 1.5? So they gave us z-score as well, 1.5, and they are asking us now to find the point, which is the diameter corresponding to the z-score. So again, this is pretty straightforward. We can directly use the z-score formula, which is equal to x minus mu by sigma, right? So we have z 1.5. The x is what we have to find. Mu is 50. Sigma is standard deviation, which is 2. Now solving this, which will be, I guess, this will be 3, I guess. 1.5 times 2 is 3. Yeah, this will be 3. X minus 50. So this will be 53. So the diameter is 53. Right? That's again pretty straightforward. Now let us verify empirical rule, which is this one, using norm.cdf. So what we can do is, so empirical rule, so again CDF is what? So if we look at the graph, we are talking about percentages. So if you have a graph like this, if you have a plot like this, if you have a curve like this is our mean, mu. And what's the question? Yeah, so if you want to verify, this is mu minus sigma, mu plus sigma, mu minus 2 sigma, mu plus 2 sigma, mu minus 3 sigma, mu plus 3 sigma. So these are the ranges. Now, in order to verify using CDF, I will have to do what? I'll have to subtract. If I want the one standard deviation value, or rather one standard deviation fraction, so I'll have to subtract all of these from mu plus 1 standard deviation. Then I'll have to subtract mu minus 1 standard deviation values, right? So from this pi, I have to remove this pi. That is when I'll get the correct proportion. So I have to do something like norm.cdf, and what is the z score here? It will be 1, right? Because it's one standard deviation, it will be -1. So I'll have to subtract from +1 to -1. You see that 68.2, that's 68%. Same with 2 standard deviations. There's our 95%, and same with 3 standard deviations. That will give us our 99.7%. So basically, I hope that was clear. We are removing. So CDF is everything from until that point, right? The definition of CDF is to get the probability, cumulative probabilities. We sum the cumulative probabilities of all these less than or equal to until that particular z-score value. So let's say till here. So from all of this, I have to remove this pi, mu minus sigma. I have to remove this stuff here. Right? I hope that was clear. Anyway, let's move on. We already saw standardization, right? We already saw standard normal distribution. It's also called as z distribution. Let's go to the final topic, percent point function. So percent point function is nothing but the inverse of CDF, cumulative distribution function. So when I say inverse, if CDF, what CDF does is we go from point to probability, right? We are trying to find the probability value. This will give us the percentage. But PPF will give us, will go from probability or percentage to the variable, the point value. So this will become clearer once we solve this question. Let me solve this question. I think this is the final question anyway. So the height of people is Gaussian. So they're already saying it's normal distribution with mean 65 inches and standard deviation 2.5. So the question, mu is 65 and sigma is 2.5. And one person says 96% people are shorter than me. So one of the guys standing in the line or in the crowd, let's just say, he's saying 96% people are shorter than him. So what is his height? The question is, what's his height? So we already have the probability, which is 0.96. Now we have to find out the point, the variable, the point value, which is his height. So as you can see, this is the PPF flow where you go from probability or the percentage to the point. So we can, since we have the probability, we can actually check the z table and get the z-score and then compute the point value, which is the height value, which is in this case it is 0.96. So it's not taking 0, so 0.96. So you see here 0.96 is in positive z-score values, it's somewhere over here, And if you see, the z-score for this is 1.7. Z will be 1.7 and the second digit is 6, 1.76. Right? So now all we have to do is substitute these values into the z-score formula. This is nothing but z equal to x minus mu by sigma. Our z-score is 1.76. X is x is what we are trying to find, minus mu is 65 by sigma is 2.5. Right? So if we calculate this, what will this be? 1.76 times 2. Okay, let's just do this in Python. I mean, where are we even? So we can do 1.76 times 2.5 plus 65. That will be 69.4. So x is, his height is 69.4 inches. So that's how you solve this through z table. Now obviously this is tedious, so there is another way using code. So we can use norm.ppf, which will give us directly. So if you see here, percent point function, inverse of CDF at q of the given random variable. If I'm not wrong, we have to pass, what do we have to pass? We are trying to find the actual value, so we'll have to pass the probability, so which is nothing but 0.96. If you do that, we pass the probability or the z-score. 1 second. 1.75 score 1.76. Nope. Wait. 0.96. No. Obviously, yes. So the flow is from probability to the point, right? So now we got, this is what? This is z-score. Yeah, this is z-score. So what we got is z. So that's the PPF. Using through PPF, we compute the z-score. And after getting z-score, we substitute in the formula, which is our z equal to x minus mu by sigma. So once we do that, we'll get our value, which is exactly, we already know the z-score, which is 1.7. Let me just put it directly. So z times our sigma is 2.5 over, no, not over, plus 65, and that gives us 69.37, which is 69.4 rounded to this one. Will get exactly the same. So that's how you compute PPF. Yeah, so that is all there is to normal distribution. I don't think I missed anything, but if I missed something, I'll probably cover it in the next class anyway. So yeah, I hope that was clear, and I'll see you in the next one.